Kavica, lahko?
Ja.
Super.
Imaš mikrofon prigan, da lahko preverimo, če deluje še z druge strani. Ne, sej tudi.
Pa. Kako se pa tu ugasne? Aha, kako bom tu pustila zaenkrat?
Zakaj se končaš?
Čakaj, to prvič, da...
Ne, drugič. Vsakeč, ko se pripravimo za pretočno predvajanje, je pač pa problem. Ne, drugič sem... Ne, imamo, sam šaltamo, ne, da... What? A ste nam še bolj čudni? Ampak, kako, zakaj je preskočil? Ne razumem, zakaj je preskočil. A bi šla ti drugače mogoče stopaš tam v Uno, pa pet na YouTube, pa preveri, če se ne sliši. Pač strasna fizikalna skupina FMF. Mislim, eno, dva je bil sem, da pač vem, ali dela zvok ali ne. Pač test. Lahko tudi tlele pogledaš se in v bistvu sam, da ne bo interference. Astrofizikalna skupina FMF. Test.
Malo zamik,
ampak... Ja, se mora biti zamik, se je vedno zamik, ne. Sam problem je, da vam je zdaj tle problem. Zakaj si čuden, YouTube? Zakaj? Damage control, ajmo. Damage control. Živijo. damage control.
Samo večjih rabov za četrtek za dan odprtih vrat, če kaj reč, to smo se zmenili.
Včeraj smo se zmenili. Jaz sem dva študenta in...
Ja, po mojem... Živja! Živja!
Zdaj sem skrbil linke, zdaj kar nekaj druga, ne?
Ja, no, vidiš, ja.
Takže za neka priložnost prišla do tega.
No, sej, včeraj ima to... ne, vse lahko, ne, stare bi pa za ogled. Ok, se to je v redu.
Zelo malo. Zelo, ja.
Sem tole pa,
Noči neba, Bereniki.
Zato treba se... Ja, logistika, da nimamo svojega avta, tako da si moramo avto spaliti. Ja, drugače pa če se da naprej kaj zmeni par mesecev. Ja.
Ne, ok, smo gor, to je važno, tle sem spremenil. Sem pač... bom zbog delna Tadeja. Mislim, obesi si...
Primerno. Primerno.
Ja, kako se to pomeni? Ok, se pravi, da te še uradno vprašam, da ti je v redu, če si na YouTubeu?
Ja, mislim, da nisi nič tak občutljivega dala. Predstavitev.
Zvok smo sprobali, tako da dela. Sam je zemika, veš, zemike tu veš ravno malo čakati. Pa Tadeja moraš pogovarjati. Ja. Sam nimam preveč Tadeja, da imam nekaj časa. Pa jaz pa še vidim tle.
Ja, tako.
Kako, mogli bi?
Tu pa še nisem bila v tej predavalnici.
Ja, ta je od tako interaktivna, tako za nepregledanje.
Ja.
Sonce misije, kar je astronomom vredno. Kaj pa so te sije, smo pa mi v posti.
Ja, to je res. Sicer jaz se zdaj moram zgodaj vstajati.
Ja, tako to pride, veš, malo biti je pa nese
Tako nenadoma se treba zgodaj vstajati in iti zgodaj s posla.
V študentska kleta sem tako zjutraj spat in takrat je pač pol kilo čokolade že šlo.
Tako. Še imate vedno opazovanja na Asjago?
Jaz nekaj dosti, ampak
Ja, ampak vseeno se mi zdi, da je nekaj posebnega iti osebno, ja, če je le možno. Ja. To pa brez dvoma. Sicer včasih malo vreme zamuštra, ampak drugače pa tako, ja. Dosti je tudi študentov zdaj.
Mislim, tako veš, kako je Bologna, pač vse to je bilo še v tvojih časih, Tadeja se štartala, se pravi, izbirne podmetje so, ampak poleg ljudi, ki so na astronomski smeri, nekaj drugi javnejo, pa seveda še magistrski študij, pa zdaj je čas biti še na skupaj,
Ja, ampak jaz sem kar nekaj različnih univerz čez dala in tudi kar nekaj učila. In res vidim, da je toliko fizike na prvi stopnji je res, res dobro za nadaljno razumevanje. Če sem primerjala svojo globino znanja matematike in fizike, tudi... Ja.
To je sicer težko, to, kar se sama spomniš, ni simptom,
Ja.
ampak v prvi fazi imamo se prednost.
Tako.
In ti koristiš. Pa tudi jaz, kaj pa vem, ljudje pol, če dobijo job v Istanbuli, so pač fiziki, čisto dobri fiziki.
Ja, tako. Tadeja, če bomo potem kaj.
Na Dunaju.
Ja. Bimet. Ja. Kako?
Bom skušala.
Super. Super. Ja, sem pa drugače maja lani doktorirala. Maja lani sem.
Maja.
Ja.
Če se spomnim, se smo se slišali.
Ja.
Aprila.
Ja, ampak za mene je bilo to med dvema porokama, med iskanjem službe. Smešano.
Ja, okej. Potem pa začnemo.
Povej mi še samo, koliko časa imam.
45 minut,
Okej.
pa imaš uro.
Super.
Lepo pozdravljeni. Z nami je danes Tadeja Veršič, doktorica iz astrofizike, je doktorirala na univerzi na Dunaju. Predtem je pa začela svojo študijsko pot tukaj, potem se upisala na Erasmus Mundus, če se prav spomnim, in je takrat v bistvu svojo magistersko pot potem naredila med Rimom,
Innsbruckom.
pa še Rim.
Rim pa Innsbruck.
In potem šla še na doktorat na univerzo na Dunaju, kjer je raziskovala, če se ne motim, kroglaste kopice v drugih ali v naši galaksiji? Drugih galaksijah, odlično. In zdaj pa dela trenutno na meteorološkem področju, vedno na Dunaju, v UBI-netu, tako da smo povabili tudi meteorologe, če pridejo zraven, da ti prisluhnejo. Skratka, jaz prepustim torej njej to predavanje, ki bo šlo od astrofizike do meteorologije. Hvala, Tadeja, da ste z nami.
Ja, najlepša hvala, da ste me povabili. Jaz sem začela tu svojo študijsko pot, tako da je zelo prijetno povabilo priti nazaj. Bom pa vse predavala v angleščini, tako da bom zdaj preskočila v angleščino. So brilliant. It takes time, and it may not be that relevant to study, but it is a very fun language to know, especially if you're on the train and you need to communicate something privately. I'm based in Vienna, and what I want to tell you a little bit today is my path from astrophysics and how I got to be a meteorological data scientist as I am now. And I made this an AI-generated really nice image that takes you from galaxy all the way to renewable power, which is something that I do right now. I do energy forecasting. So today what I would like to tell you a little bit is the dark matter halos that I've studied during my PhD. There's one really interesting piece of work, an investigation that I did during my PhD, and I would like to highlight that. Then I would like to introduce a little bit the group and all the research possibilities in Vienna, in case you're interested for future collaborations. And then I would like to segue a little bit into my personal journey, into how I got interested into climate change that ultimately led me to this position of meteorological data scientists. So let's start with why we are here. We are here because we're interested in astrophysics. So dark matter halos, and in particular how we can probe dark matter halos with dynamical tracers is what I studied during my PhD. You can see here, this is from the TNG simulations, what is the difference in the spatial distribution of the stellar or baryonic component that we can observe and dark matter that is not directly observed. So we need to use these baryonic tracers in order to uncover where dark matter is distributed or the total mass distribution. So I like to start out with this stellar halo mass relation, where you see the halo mass, or the total dynamical mass of a gravitationally bound system, and the ratio between the stellar mass and this halo mass. So this is kind of tells you the efficiency, how efficient are dark halos in transforming the baryons into stars. And you see here that they peak around Milky Way type galaxies, and then they drop further on. So by probing how dark matter is actually distributed, we can actually constrain all these different analytical, semi-analytical models of of what dark matter actually is. The problem with studying dark matter, as I shown before, is that it dominates the mass budget, mainly on large galactic radii that are very difficult to probe, especially in external galaxy. And I use here dynamical modeling is the best tool that we have to infer its distribution on the largest scales, with lensing probing only the really inner regions, but with dynamical modeling we can go much further out. Of course, stars are very centrally concentrated, but we have other tracers, other potential tracers that we can identify in the halos of galaxies. And these are globular clusters, and they group together in what we call globular cluster systems. So what are they? These globular clusters are very old stellar structures. They have around 10 to the 4, 10 to the 6 stars packed really densely together, so we can observe them out to 50 megaparsecs, so in the nearby local groups and some of the nearby clusters like the Virgo and the Fornax cluster. They are found, they're ubiquitous. All of the galaxy halos have these, even the least massive ones, and they have some very, very interesting properties, namely that the distribution in terms of magnitude that can be mapped to mass because of their old age is very, very universal, and the mass of the globular cluster system, so all of the different globular clusters that are in the halo of an individual galaxy, have a strong relation with the halo mass. So the total mass, halo mass of the galaxy, the baryonic and the dark matter mass, is very tightly correlated then with the globular cluster system, which indicates like co-evolution of these systems. So I used all of these properties, the fact that the mass in the globular cluster system is tightly correlated with the halo mass, as well as the fact that that the mass or the luminosity distribution of globular clusters has this shape that is for most of the galaxies, the same for most of the galaxies. And another interesting property that these observed globular cluster systems have is something called the bimodal color distribution. What this means is that because of their old age, color can be linked directly to their metallicity. And lower metallicity means that these systems formed from a more pristine or less metal-enriched environment. So by understanding these differences, by having these color bimodality means that lower, more bluer, more metal poor globular clusters are actually formed in lower mass system where the metal enrichment hasn't been that strong, while the metal-rich or bluer globular clusters were formed in more massive system where the metal enrichment and the star formation was faster. So we can use all of these properties of the globular clusters in order to model globular cluster systems, and in this case, in the study that I will show, is to not just infer the global properties, such as what is the total mass, or what is even the radial distribution, which is what mostly people have done, but actually to look at how is dark matter distributed in galaxies. I have an example here of this is NGC 5128, or the Centaurus A galaxy. It's a very, very nice galaxy that I've studied, and I'm just showing the picture here. But what do we mean by shape? So we see here that this galaxy actually is slightly elongated in this direction. It has this polar disk. So why would dark matter be spherical, as it's considered right now in many dynamical modeling? And actually from the hydrodynamic simulations, there is evidence that depending on whether you have only dark matter or only or add baryonic component, this will change or alter how what is the shape of dark matter halo on large scales. So here I'm just plotting. I will show the constraints on the dark matter halos, and that it's actually possible to constrain dark matter halos. And here, this is what is a variable called triaxiality. And you can think if triaxiality is very low, so in this extreme example, you have an oblate system that's like a squashed ball. And if you have a prolate, then you have an extended like an American football. So these are kind of the extreme examples of a triaxial system, and anything in between is like a general triaxiality. And you see from the simulations, we do expect these systems to deviate strongly from spherical symmetry. So by constraining what is actually observationally the shape of dark matter halos, we can also constrain what are the prescriptions that we use in our hydrodynamic simulation, and is our theory of dark matter correct? I've shown you a little bit before of this central region of the Centaurus A galaxy, and you can see here now in this intensity of, so actually it's the number count of red giant branch, of how extended actually the stellar halo, just the stellar halo of this galaxy is. Actually, the stars extend much further out than just this inner few effective radii. Of course, this galaxy is really, really close by, so we have the possibility with HST to probe these low density environments. But if we go further out, if we want to extend our sample, then we cannot rely on the counts of red giant branch stars, but we have to use other sources. So this is a relatively massive galaxy, 10 to the 11. It has a lot of halo tracers, a lot of globular clusters, and is expected to have around 1,500 globular clusters spread all throughout this halo. This is, I think, around 150 kiloparsec. So this is really, really far out into the halo. One of the interesting features that you can also see is that the halo isn't uniform, but we see some overdensity, some streams. This and some shells, this indicates that this halo might not be dynamically relaxed, which is something that we have to keep in mind when doing dynamical modeling. The data that in my work that I've used is I used very deep photometry from the DCAM camera, and I use the globular cluster luminosity function in order to further clean this data set. And I had kinematics for around 500 globular clusters, and you can see here the color dots are the actual velocities and how the globular clusters rotate and move within the halo within 40 kiloparsec. And in the background, what you see is actually a smooth velocity field from the planetary nebulae, and you see this that this is not symmetric. The position, the kinematic position angle is not shaped that indicates actually triaxiality. So even in the planetary nebulae of this specific galaxy, we do have evidence that this is a good galaxy to target if we want to detect deviations in the potential, in the gravitational potential from spherical symmetry. Any questions up to now?
Yeah, I
Yeah.
have one.
Go for it.
Basically, from your global cluster luminosity function, right? You say you clean the sample, and I wasn't quite understanding how you can clean the sample. I mean, I guess from theory you would know what the luminosity function should look like, but that doesn't mean that it actually looks like that, right?
Exactly, but that is the best, the best thing that you can do. Of course, if you want to really, really clean all the foreground or background components, so all the foreground stars effectively that belong to the Milky Way, you need the kinematics. That's really the only way. But in order to do dynamical modeling, you need to have a good handle on what is the spatial distribution of the sources. And you know that at a very high mass or high luminosity end, your sample is more likely to be complete.
Yeah.
So you look at, so this is the theoretical globular cluster luminosity function, and in gray is the observed one, and you see where they start to deviate. So where they start to deviate significantly, that's the first order cleaning that I did.
You only take the brighter ones.
Exactly, exactly.
And how do you get your kinematic data from them? Because you were saying you use imaging, but where do you have spectroscopic follow-up then? Or?
This would be a whole PhD if I did that, and this was just one aspect. So I got actually the photometry. This was from DCAM, and it was from the Taylor et al. 2017, and kinematics I got from Hughes et al. 2021. This galaxy has been observed so many times that this is actually a compilation. This is DCAM, and this is a compilation of very, very different ones.
Okay.
Yeah.
I also have a question.
Perfect.
Probably a stupid one, but
No worries.
go to the slide where you have this one.
Yeah.
I was quite shocked.
Yeah.
So what I see there for the Centaurus A is a disk and jets.
Mm-hmm.
Is that correct?
No. I mean, yes and no, but maybe this one is easier. So the stellar body is elongated like this, and this is a polar disk, actually. It has a polar disk, and then the jets perpendicular to it. So the jets are in the direction of the major axis of this galaxy, which is very cool. But I did not go further into detail on this.
So what's the main stellar density then?
It is elongated along this. It's an elliptical galaxy, so this disk most likely is a result of a merger.
Okay.
And this is dust.
Yeah, this is dust. This is dust, a dusty. Yeah.
Nevertheless, if you go back to that one then, this halo where you detect the giants, right, around this galaxy, I mean, around the disk, let's say, the main region is huge, I would say, compared to what we imagine as the halo of our galaxy. Am I correct in saying that?
This is the stellar halo, yeah.
Yes.
Yeah.
If you imagine the Milky Way being in there, is our stellar halo that large?
Whether it's that bright is a different thing, but it's also...
Do we detect giants to those 10 times the distance of our Milky Way disk? Is the question.
I think so, but I'm not the person to ask about this. I think that red giants is not generally what people look, because there you have a problem in the Milky Way. You have a problem with cleaning, so usually the red clump stars are what, or RR Lyrae is what people detect, and I think they go up to 200 kiloparsec in the Milky Way. But but they go really, really far out with these either red clump stars or RR Lyrae is what people usually use, because photometrically they're easier to clean from the whole sample.
Because because that would be beyond the Magellan clouds, right, for us.
Yeah, yeah, yeah.
And I don't consider that the halo of our galaxy anymore.
But it's very different when our disk is cold. It's very, I mean, it's not a polar disk. So as Tadeja said, this is probably a remnant of some merger, right? It's probably
So maybe that merger.
so that this is
throughout
not
the-
part. I mean, it's not representative of the full galaxy.
Yeah, it's not analogous to the disk that you imagine for the Milky Way or the Andromeda.
Sure.
Yeah, yeah.
Okay. Thanks.
Maybe I missed it when you mentioned it, but why did you use red giants then?
This is just an illustration. I did not use red giants. You can observe them photometrically, but they're too far, too faint to get kinematics. So what I use are globular clusters. These are very dense packets of stars. I think some of these very bright sources are globular clusters, and these are actually then dwarf galaxies.
But this is actual data of red giants.
Yeah, this is actual data of red giants.
So those are the satellites then, like the Magellan clouds for us.
Yeah, yeah, exactly. And you can see this one dissolving and there's
Oh, okay.
yeah.
One more question. So one slide back.
Uh-huh.
So when do you get a sphere? When t is 1/2 or?
A sphere is actually undetermined in this space,
Okay.
but the sphere is a very perfect example that you will never really get. So in this, because this would be then 1 in sphere, Q and A are 1 for obvious reasons, and then you have here division by 0. So it's infinity. But that is like such an extreme case that, yes, okay, great, very well. So, yes, great. So we have good evidence. Now we understand our data, our photometric kinematic data, and we understand how that there is evidence that this is actually a triaxial galaxy. So what I use are Jeans equations in order to constrain the flattening. So I use axisymmetric Jeans modeling, which still is sensitive only to 2 extreme cases, either prolate or oblate. There's currently no triaxial code for discrete tracers. What does discrete means? It means that at the position of each of these dots, we assume a distribution of how line of sight velocity is distributed, and we use this point to constrain it. And by combined constraint of 400, 500 sources, we can build a good likelihood and constrain our parameters. So yeah. So I use this in, so we can only probe 2 extreme examples, either flattened or an elongated case. And what I found, because I separately modeled the blue and the red, so these are the constraints on the total halo mass, on the stellar mass to light ratio, and the flattening, and these are the 2 the blue and the red populations, because they have slightly different kinematics and spatial distributions. They can be considered as independent dynamical probes of the same potential. So you see that in terms of the total halo mass, they agree quite well. The stellar mass to light ratio is slightly different, and in the flattening, they also quite agree. They agree quite well. And what I find actually is that this galaxy is hosted in a prolate halo, which would mean that it's elongated along the minor axis of the stellar component, which is something that was a bit unusual. And it's not so simple. So I put the star here of my results. Of course, this is all in this framework of axisymmetric modeling, which means that we only can detect one or the other because of the limitations in our modeling approach. Still, what this method demonstrates is that there is like the flattening of one, which would be spherical, is strongly disfavored. So now I wanted to understand is what does that mean? Could it be our, what does it mean that within the context of axisymmetric modeling, the flattening that I recover, this elongation along the stellar minus minor axis is this common? Is this likely? If we look at the hydrodynamic simulations, how often do we find such configurations? Because it could be quite unusual that you have such extreme misalignment between the major axis of dark matter and the stellar component. So we looked at two different simulations, the illustrious simulations and the magneticum simulations, and in all cases we found just one galaxy. In both the ones that are similar in terms of star formation rate and mass, as well as the environment, that it's in a bit more common, like not densely packed galaxy clusters. And in both cases, we just find one galaxy. And this one galaxy, in both cases, actually shows disturbed morphology in their kinematics. So you see this is the projected velocity. You see some rotation in this direction and some rotation in this direction, or I forget always. But you see some rotation along the major and minor axis, as well as the velocity dispersion profile is not smooth, which all suggests that these examples that we find that have misalignment between dark matter and stellar major axis actually do show sign of disturbed morphology and recent merger. So if such misalignment occurs in simulations, it's most likely due to a transient feature. But one of the possibilities, it's unlikely that this is not representative of what we see in the simulations. So maybe there's something wrong with our dynamical modeling approach, that we're really reaching the limits of our axisymmetric assumption. And here I just show what is the smooth velocity field of the globular clusters, and you see the rotation along the major or semi-major and semi-minor axis, and dispersion profile that is not smooth, with a peak in the center and a gradual drop towards the outskirts. And if we actually look at some mock data sets, we can see that actually this is an example of a triaxial galaxy with a map of the line of sight velocity distribution, and you see this rotation along the major and minor axis that is also present in the globular clusters. So actually it's most likely that the kind of flattening, the misalignment that came out in the modeling is due to the modeling assumptions, and we really need to go into triaxial modeling. Nonetheless, all this investigation does show that globular cluster systems and the dynamical modeling is sensitive to deviations from spherical symmetry. And it would be fantastic if we could extend this work and probe more galaxies and not just the one, to get a full census on what is the spatial distribution of dark matter, not just radial, just in terms of radius, but also in terms of deviations from spherical symmetry. So this, I hope, will help you a little bit to understand what is done for astrophysics in Vienna, and specifically the stellar dynamics group that I've been embedded. So now we will change tracks a little bit, and we'll look at what are all the different research topics, questions that are investigated at the University of Vienna, and there's another institute. University of Vienna actually has quite a lot of research group with many different topics of investigations, going from cosmology to galaxies to stellar system, really looking into the Milky Way, of how the stars and the young massive clusters are distributed, the early phases and the late phases of stellar evolution, looking into how these young massive, pre-main sequence stars are distributed, where they are, as well as looking into the AGB phase, so the asymptotic giant branch star phase. But there's also quite a lively group on planets and exoplanets, where they study how how do the protoplanetary disks evolve, as well as how do the atmospheres of planets form and how they survive. So these are very broad research topics. There is another institute that has been growing recently, and that's the Institute of Science and Technology in Austria, and they specialize in interdisciplinary research. So very often, people that come in to astrophysics, they also bring either a data science component or an astrobiology component. So if you're interested in some interdisciplinary work, this is a nice place to look at. So let's have a look a little bit into stellar dynamics, the group that I'm most familiar with and kind of overlaps between galaxies and stellar systems. It's a very big group that keeps on growing, and it's a very lively environment to be in. It studies many different concepts, both from the kinematics, from the observations and modeling. So here I would just like to highlight some of the recent work that was done by the group. Katja Farion, she does a lot on observations with integral field units. These are these are images effectively in all different wavelengths. So each of this pixel is actually a whole spectrum. So you can get both photometry and kinematics at once. And Katja has recently joined the group from ESA, where she's worked on James Webb as well. And she's recently done an investigation around an ultra-diffuse galaxy, where you can see in age and in metallicity a bimodality, which is very interesting. So very large sample of low metallicity globular clusters and high metallicity globular clusters. So this galaxy, this ultra-diffuse galaxy, is quite complex. And if you're interested, she's always excited to talk more about it. Another point when it comes to observations, deriving kinematics, metallicities, and ages of a stellar population is the work done by Jesus and Pershin. What they've done is they've tried to go away from a simple assumption on how stars move within the galaxy. I showed you before just mean velocities and velocity dispersion. That's usually all that you can do. But this is an example of a galaxy that has a contra-rotating component. So it has two disks that are contra-rotating. So how do you describe that in terms of only two moments of a Gaussian line of sight velocity distribution? You cannot. Your dispersion will be inflated. Your mass measurements will be biased. And this is actually, if we look at these axes, we see this is the central region, and then we see the prominent two peaks. And what up to now has been done in the literature is to fit one Gaussian to it, but now they're developing methods to fit actually two Gaussians and detect these contra-rotating disks in these galaxies. It's very hard to see that this galaxy has a contra-rotating disk, but if you look at its kinematics, how stars are actually moving, you can detect it. In terms of dynamics, it's not just the axisymmetric genes modeling that I have demonstrated, but their expertise in this group, and they're working on many different topics. So this discrete genes modeling that is based on collisionless Boltzmann equation and assumption of steady state and very rigid assumption on the symmetry of the system is used quite a lot for its simplicity and to how many different data because it doesn't require such precise data to model, and it can be used for discrete data sets like individual stars instead of observing a line of sight velocity distribution. So this is a recent example from Anya, where she modeled the really inner a few tens of parsecs of our galaxy. And she could recover the mass of the central black hole much better than previous studies with the stellar kinematics have been able to. So this discrete approach, it can be very, very powerful when applied to the discrete data sets, because it's not affected by arbitrary spatial binning and any interloopers when you have multiple populations in the same spatial extent. Another interesting work was done by Alice Zocchi on line pi models. These are distribution function models, so another family of models. When you have a good understanding of what your distribution is in space and in kinematics, distribution function models is what one can work on, and she worked on the internal dynamics of globular clusters, so really looking at within the globular clusters how the stars are moving and how they're distributed. The most flexible of all approaches is what is called the Schwarzschild orbit superposition model. And what it enables is when you have an image and you construct the mean velocity field and the velocity dispersion field, it enables you to study what is the orbital distribution. So where are stars as a function of radius? How many stars are on very random orbits, these hot orbits with very low values of circularity? Where do we see the disk? You see this galaxy has a nice disk. So you see the disk is distributed over all radii, and there's also some potential contra-rotating component. And by investigating plots like this, we can also probe what is the merger history of these galaxies. These orbits, these Schwarzschild orbit superposition models are intrinsically triaxial, and they require quite a high quality of data set, so you're limited in spatial extent of where you can use it. Of course, in order to do dynamical modeling, you have to know what the stellar populations you have, and there's a big group that studies also what is the stellar populations, what is the distribution of the stellar populations, and really constraining many of the theoretical properties of where are the in situ stars distributed in the simulations, and where is the ex situ or the accreted component, where is it located, and you see that it becomes dominant in the outskirts where the mergers mostly deposit their material. So Alina Bucher is the one who's doing a lot of analysis on this work at the University of Vienna. There's another interesting problem that arose in the field of globular clusters and their formation, and that is presence of metallicity anomalous globular stars within the globular clusters. And Laurent Freor did an analysis of what could be the source of this excess metallicity. This kind of brings me, Laurent is quite a close friend of mine, and during COVID we were both quite upset with the world, with being isolated, etc. We saw climate change, and we started a project called Please with some other friends in the group. So we became quite frustrated over how, over the degree of inaction we saw in the world and how climate change was communicated. Climate change is very often communicated with these thermometers that say, oh, yes, we're almost at our 1.5 degree limit, that is the Paris Agreement, but what does that actually mean for us? What does that mean? So we were a bit frustrated how climate change was communicated. So we developed with a group of other PhD students something called the Please Index. And now I'll move to climate research and meteorology. So we did a bit of a research project aimed at constructing an index that would more efficiently communicate how our lives, the quality of our lives will be impacted by climate change. So the way we did that, we based it on Maslow's pyramid of needs. When it's these, the bottom layer of the pyramid are these basic needs. We need to be warm, we need to be well fed, and once we're well fed and warm, then we move up to higher level needs. And the highest level that we probed was the esteem needs. We found in the literature a mapping between these psychological needs, so these, this Maslow's pyramid of needs, and climate variables, where we mapped it to poverty, life expectancy, employment, and satisfaction with life. And all of these, we then further, we did some research and we mapped it to parameters that will be changed as a result of climate change. We will have higher humidity, higher temperature, more heat waves, more consecutive dry days, and all of this will impact our quality of life effectively. So we now go from these temperatures, we are at 1.5 degree warming, and we mapped it to something that's maybe a bit more tangible, in the sense that the higher you are on this pyramid, the better the quality of your life will be. We did that for many countries, and we then looked at, based on the different projections of climate change, how much we will, what are the policy, how much we will curtail or continue to emit CO2, how this will impact our position. So we can look at some historic data from 2010 and see, okay, this is how the world looks like in terms of peace index, where 1 is very low, so high poverty, low satisfaction with life, to high, which is 4, which is low poverty, high satisfaction with life. And you can see US, Europe, Australia, they all rank very high on this index. And of course, countries like in Africa, in South Asia, rank lower on this index. So how will now this situation change when we compare from going from 2010 to 2050? These RCP are 2 different models of climate change, how much warming we will have as a result of here there will be less CO2 emission, and this is more CO2 emission. And you see red is negative, green is positive, and you see that in both cases, Europe, the US, Australia will go down in these please index, meaning the quality of life will drop. But if we continue to emit more, then this change will be even stronger. So yeah, this is what brought me into climate change. We published actually this work in Proceedings. And that is why after my PhD, I wanted to go a little bit into meteorology, seeing how I can make, with the skills that I have, how I can make an impact on the world. And I became a meteorological data scientist, which not sure what exactly it means, but it's a fancy title that I have. So UbiMet, I work in a company called UbiMet that actually aims at, focuses on severe weather as well as energy meteorology. So we do energy meteorology, we predict severe weather events, we help the ÖBB, the Deutsche Bahn, to keep their trains running, to know which station is more likely to be affected by snow or flood or the fire. So this is mainly what the company does, and there's a lot of research actually, and a lot of different data streams that we need for that. So there's a lot of different data now that I get to play with, like satellite data, where lightning strikes are happening. There's radar data, weather stations. Really, there's a lot of data that is processed every day. But not just data, also we have numerical weather predictions, of course. These are then the basis of how we forecast. If we don't have any predictions, any model predictions, then we will not be able to know what weather will be like today, tomorrow, and the floods then can really damage a lot and affect people. So I'm almost out of time. So I will go very briefly over the energy meteorology part, which is what I do there. And energy meteorology is actually a new field, and it is quite important because the renewable resources, solar and wind, are very variable. They're affected by the clouds, by the wind, and in order to ensure that the electricity grid remains stable, we have to have good models. And here, what I do is I model, I take as input the numeric weather models, the observations, and build a physical and machine learning model in order to, here you see the yellow line, the pink line, which is the observations, and in the blue are the different kinds of machine learning models that in this work, for example, they did. So you can see which kind of models are better able to forecast how much sun, this is solar power production, you see the diurnal cycle, how much solar production will be done. Of course, there are many challenges, but understanding, having a good domain knowledge in physics is hugely helpful. Another important aspect is also severe weather warning, and in this aspect, I look at how the winds are moving based on satellite images and how the lightning density is distributed in order to better forecast what is the probability of a severe storm. So yes, I will leave you here with my conclusions. Thank you all very much for listening, and I hope you found it interesting. Go for it.
I have a question on the first topic.
Yeah.
So it's you were saying you talked about this transient phenomenon, what you think is transient phenomenon of the misalignment between the baryonic and the dark matter axis and halos. And I was wondering, because you said you were studying magnetic luminosity simulations, and I was wondering if you have any idea of the timescales for the phenomenon. So specifically, like, did you look at different snapshots of the simulation or just the final?
And we just look at the final, because it was like an addition. But that was our next thing that we would look at, how long they persist. Because even getting where exactly it is, you have to be very specific to select the analogous radius. Where is our data located? Where is actually, in which radius are we constraining in SENE this misalignment, and then looking at to analogous, yeah, but would definitely be a next part, how common it is. Yeah.
So related to this, I find when I looked at your axis ratio, it was kind of striking to me because 1.45 seems very large, but then I looked at your error bars and I see they're large as well. So when you select your analogs, are you seeing, are you requiring the axis ratio to be exactly 1.45, or are you allowing for this range that you have there within your error bars?
There was no requirement on the axis ratio per se, only on the angle.
Okay, so you're just looking for misalignment rather
exactly.
than just, because even, at face value, this is quite an elongated dark matter halo. It's very, very tricky to get such an elongation, so it would be good to look in simulations also for such an elongation. And in particular, when you're merging two halos, like two round halos close together create a very elongated dark matter halo for a moment. So that's why that would be also interesting to see.
Absolutely. This data set, the kinematic data set, was within 40 kiloparsec, and that's 6 effective radii. So we are still not going all the way up to the halo because the globular clusters there are not relaxed.
Okay.
So including those that at 100 kiloparsec would be dangerous. So this is really within the 40 kiloparsec. So this kind of large scale, like for example, like the effect of this stream, I think it's unlikely. But this galaxy doesn't have a neighbor, a prominent. It lives quite in isolation.
Well, but it had a merger history,
Yeah,
right?
absolutely.
I think. And
Yeah.
so that's
Yeah.
something to be careful of.
Yeah.
But indeed, yeah. Now that you gave me the scales, I guess you're probing more the inner part, which is also affected by variance, rather than just the pure dark matter halo.
Yeah.
Elongation.
Yeah, the problem is when you try to really go out there, the dynamical timescales become so long you cannot really be sure that this isn't just the first infall and your tracer is actually not relaxed, and then you will naturally get an overinflation of the velocities at those radii.
Yeah. So maybe, I'm like, when this is this metrological part, yeah, so this is like a private company you work at?
Yeah, it's a private company.
And it's like, how many people are working there?
It's around, I think, 150.
Uh-huh.
A lot of them.
Huge company then, yeah.
A lot of them is on infrastructure, but there are, I think, around 20 operational forecasters that are really operational metrologists, and the R&D team, we in the R&D team are around 8, and we really focus only on research, and then the implementation is done by someone else.
Oh, okay.
Yeah.
And so you saw correctly, I guess you don't have your own like models, like you use the global model from somebody else, or I mean, it's probably too expensive to run, yeah.
There is one model, but it's only on Europe for obvious reason.
Okay.
Yeah, we do have one local model, but it's only on Europe. And then there's a lot of like reanalysis to map, a lot of like house reanalysis to map this very coarse ECMWF, so the European Center for Mid-Range Weather Forecasting, to map it locally, especially in Austria, because of all the mountains. It's not trivial how you map this grid that is like 5 kilometers. In 5 kilometers, you have many mountains. So that is.
So you don't do only for Germany, you also do for Austria?
Yeah, because it's an Austrian company.
Oh, it's also a German company. Aha, okay.
No,
German,
it's Austrian. Yeah.
Vienna.
Yeah, Vienna.
Yeah, it's interesting for me because in Slovenia we don't have really a private company who would do such a thing, because like these energy companies who need this meteorological knowledge, they simply hire our, let's say, meteorologists to do this energy meteorology stuff. Yeah. So it's interesting to see how this works in other countries. But there are multiple such companies in Austria, or you don't know?
That do energy metrology. I think that there is energy metrology, and I think we are one of the very few. And then it's a lot with energy trading, which I'm not that personally interested in.
Yeah.
So you have to buy and sell electricity. But many of our clients actually come from Germany, because Austria has a lot of rivers, and that is very stable. But Germany has a lot of wind and solar power production, and they need that a lot. Yeah. But I don't know of other Austrian. I know there are Austrian companies that do energy trading, but not energy metrology.
Okay, thank you.
But how do the timescales here? Because I imagine, to avert against flood or against snow, the timescale is of the order of 24 hours. That's fine, okay? But for the solar power, it's minutes, because you need to put up a power plant to compensate for the clouds or whatever. I mean, so do you do some, AI prediction, or you just do plain models? I mean, how you propagate for another hour, for another 2 hours, what will happen? Because, okay, you have past data, I mean, do you simply project, or how you do it?
Yeah, so there are many different ways of how you do this, but you have to always look at from the point of view of what is needed.
Okay.
So what they need is 1 hour, 1 day before, 2 days before, so that they can plan, so that the grid operators can plan how much they have to balance, which power plant has to be shut down, how much biomass has to be turned on, etc. There we always use the numeric weather models as the basis, and they are the ones that will propagate, that we use as a basis, and then to pin it down to local variability, that we use then machine learning approaches.
Scales of Europe 1 day, not
Yeah,
lower.
exactly. 1 day, it's 1 day because that's what is that's what is needed to ensure the grid stability. Yeah.
So then besides this shuffling around of electricity from different sources and so on, because you have peaks and so on, do you also do any work on storing the energy? Like storage systems?
I don't do that. I don't do that myself. But yes, there are certain storage systems. It can either be hydro storage that you pump up water, or that it's battery stored. But those capacities are quite limited. Yeah.
I'm wondering about the water pumping up.
Yeah. Especially like at night.
Yeah, you get those in Austria?
Yeah, quite a lot.
Okay.
Yeah, but what does a lot mean? Because we always want to be similar, and we are orders of magnitude down, right? So I just wonder, is it something you can do for hours or for a day?
That's a good point that I never actually checked. There is this, yeah.
You have one in Slovenia, right? Only one, I guess.
Yes, I can tell
When
you.
you fly to Munich, you always fly across these artificial lakes on the tops of the mountain.
Yeah, so I can tell you that the capacity for the hydro capacity is twice as large as the hydro storage that they have in Austria. And in Slovenia, if that information exists, hydro storage is around 1/4 of the capacity available from hydropower. Yeah. Yeah, I don't have.
Efficient data scientist.
I know where to find the information. Yeah.
I think we have to leave the,
Yeah. Yeah.
So, thank you again.
Yeah.